In the first video, Learn Go in 12 minutes, we had a very quick look at the main features of the language, so you could get going straight away. One thing I didn't talk about though was the support for concurrency that Go has. This is a really big part of Go, it's a big selling point and a reason why a lot of people choose the language, so I thought it deserved its own video. It's worth understanding that concurrency is not quite the same as Learn Go in 12 minutes. We had a very quick look at the main features of run things in parallel means to run two things at exactly the same time. This is what happens on a multi-core processor. You have one core doing one thing and another core doing a different thing, both simultaneously. Typically though, the lines of code that make up a program have to run in the right order, which makes it hard to parallelize and execute two lines at the same time. So concurrency is about breaking up a program into independently executing tasks that could potentially run at the same time and still getting the right result at the end. So a concurrent program is one that can be parallelized. We're not going to concern ourselves with what is happening at the CPU level and whether something is running on multiple cores or not. The Go runtime and the operating system will take care of it for us. We can concentrate on the structure of our program and using the tools that Go gives us to make our code concurrent. So I've got a text editor. I'm going to write a really simple function called count. It's going to take a string as an argument, and in an infinite for loop that starts at 1 and just loops forever counting up, I'm going to output the number that we're at and the string that we passed in. And then I'm just going to sleep for half a second. And I can count sheep, and then I'll make a call to count fish afterwards. So this is a synchronous program, there's no concurrency here. It's going to execute the count function, and it's going to wait for it to finish before moving on to the next line. But the count function never finishes, so it's just going to count sheep forever and never get to the fish. So I'll just do that until I kill it. If, however, we call the function with the word go in front of it, it won't wait for it to finish before moving on to the next line. It'll say, go and run this function in the background, and then continue to the next line immediately. And this creates what is called a go routine, and that go routine will run concurrently. So we now actually have two go routines. The main function with the main execution path of the program is a go routine, and now this new one that we've created explicitly. So these will both run side by side, and we see now it counts fish and it counts sheep. Go routines are very efficient. It's okay to make tens, hundreds, even thousands of Go routines, but bear in mind that you can't make a program infinitely fast by adding more and more concurrent Go routines, because ultimately you are constrained by how many cores that your CPU has. I'm going to make one tiny change to this program and run both count functions as Go routines. Now you might expect this to do exactly the same as before, and you'd be almost right, but we get a very different result. We don't get anything. So what has happened? Well, in Go, when the main Go routine finishes, the program exits, regardless of what any other Go routines might be doing. Previously, the main Go routine never finished because it would have this infinite for loop. In it. But now we've pushed that loop into its own Go routine, so the main function will continue immediately to the next line. But there are no more lines of code, so it's done and the program terminates, and the Go routines that we've created ourselves haven't had time to do anything. If we were to sleep for 2 seconds here, you'll see it now outputs for 2 seconds and then it terminates. You'll often see people add a call to fmt.scanline at the end of the main function to fix this problem, and this will stop the main function from immediately terminating because it'll wait. This is a blocking call. It'll wait for user input. So this gives our Go routines time to execute, and it's going to keep doing this until I press enter. And at that point, it'll move on and the main function will finish and the program will exit again. In reality though, this is not a very useful solution because it does require manual user input. What we can do instead is use a wait group. I'm going to import the sync package from the standard library. And let's just alter our program so we have one call to count, and let's just count up to 5. To use a wait group, I'm first going to create one. And it's nothing scary, it's just a counter. And I'm going to increment it by 1 to say that I have one Go routine to wait for. And it doesn't do any magic here, it's up to me to increment it. The next step is to decrement the counter when the Go routine finishes. So after this for loop, I want to decrement the counter. Now I could pass a pointer to the wait group, to the count function, but I don't think it's really the responsibility of count to deal with this. So instead, I'm going to wrap the call to count in an anonymous function. This syntax creates a function and then immediately invokes it. So this will still run as a Go routine, and inside here, I'm going to call count again. And then afterwards, I'm going to call wg.done. Since we've created this function inline, we have access to that wg variable, which is convenient, and done literally just decrements the counter by 1. So all we have so far is a counter of how many Go routines are running. The useful bit now is to call wait at the end of the main function. This will block until the counter is 0, so if any Go routines haven't finished, it'll wait. So now it's going to count to 5, count will return, we'll call done, which will decrement the counter, and then this wait will be like, oh, the counter's at 0, and allow the code to continue, and the program terminates. Really easy to use. So that's how to create a Go routine. Really simple but not massively useful so far. What we need next are channels. A channel is a way for Go routines to communicate with each other. So far the count function has just been outputting directly to the terminal, but what if we wanted to communicate back to the main Go routine? Well, we can accept a channel as an argument. And it's like a pipe through which you can send a message or receive a message. Channels have a type as well, so this one will be a string channel and will only be able to pass messages that are strings. Any type works though, you can even send channels through channels. So instead of outputting thing to the terminal, I'm going to use this arrow syntax to send the value of thing over the channel. So an arrow pointing into the channel name will send a message. Gonna get rid of the wait group stuff now. So nice simple concurrent call to count, and now we need to pass the channel in. So first we can make one using the make function. Pass that to count, and then we can use an arrow coming out of the channel name to receive a message from the channel. So this is going to receive one message, output sheep once, and then terminate. And it's important to understand that sending and receiving are blocking operations. When you try to receive something, you have to wait for there to be a value there to receive. Similarly, when you're sending a message, it'll wait until a receiver is ready to receive. So we can see it does what we expect, it outputs sheep. And this blocking nature of channels allows us to use them to synchronize Go routines. Imagine you have two independent Go routines. Each line here is a line of code. We don't really care what it is, except down here we receive on a channel. And over in this Go routine, we send on the channel. When they both execute, sometimes one will stop and start and the other will stop and start. They might be executing different code. They won't stay synchronized at all. But when this Go routine on the left tries to receive on the channel, it'll stop and wait until something is sent. And at some point, the other Go routine will reach the line where it tries to send, and then they'll be able to communicate through this channel. So at this precise moment, they're both at this communication point. So we're communicating and we're synchronizing, which is an important concept. Back to the code. This just receives one message. If we wanted to receive all of them, then we could wrap this in a for loop. So this does what we expect, but then it gets a fatal error. We get deadlock. This is because the count function is finished, but the main function is still waiting to receive on the channel, but nothing else is ever going to send a message on the channel, so it'll be waiting forever. The program will never terminate. Go is able to detect this problem at runtime, not at compile time. The output's cheap, and this blocking nature of channels. So a nice simple concurrent call to count, and now we need to pass the channel in. So first we can make one using the make function. Pass that to count, and then we can use an arrow coming out of the channel name to receive a message from the channel. So this is going to receive one message, output sheep once, and then terminate. And it's important to understand that sending and receiving are blocking operations. When you try to receive something, you have to wait for there to be a value there to receive. Similarly, when you're sending a message, it'll wait until a receiver is ready to receive. So we can see it does what we expect, it outputs sheep, and this blocking nature of channels allows us to use them to synchronize Go routines. Imagine you have two independent Go routines. Each line here is a line of code. We don't really care what it is, except down here we receive on a channel, and over in this Go routine we send on the channel. When they both execute, sometimes one will stop and start and the other will stop and start. They might be executing different code. They won't stay synchronized at all. But when this Go routine on the left tries to receive on the channel, it'll stop and wait until something is sent. And at some point, the other Go routine will reach the line where it tries to send, and then they'll be able to communicate through this channel. So at this precise moment, they're both at this communication point. So we're communicating and we're synchronizing, which is an important concept. Back to the code. This just receives one message. If we wanted to receive all of them, then we could wrap this in a for loop. So this does what we expect, but then it gets a fatal error. We get deadlock. This is because the count function is finished, but the main function is still waiting to receive on the channel. But nothing else is ever going to send a message on the channel, so it'll be waiting forever. The program will never terminate. Go is able to detect this problem at runtime, not at compile time. It hasn't solved the halting problem, but when it actually happens, it can see that Go routines aren't making any progress. To solve this, we can close the channel. As a sender, if we're finished sending and we don't need the channel anymore, we can close it. If you are the receiver, you shouldn't ever close a channel because you don't know whether the sender is finished or not. If you close the channel prematurely and then the sender tries to send on that closed channel, it'll cause an error, it'll panic. But it's okay for the count function here to close the channel because it knows that it's done and it's not going to use it anymore. When we receive on the channel, we can actually receive a second value which tells us whether the channel is still open. If it's not open, if it's been closed, then we can break out of this for loop. So now we don't get the deadlock anymore, and there's actually a slightly nicer way we can do this in Go by iterating over the range of a channel. So this will keep receiving messages and putting the value into this message variable here until the channel is closed. So then we don't need to manually check that it's closed anymore. Exactly the same result, just a bit of syntactic sugar. So we've seen so far that sending to a channel is a blocking operation. To demonstrate the constraints of this, I'm going to do something really simple. I'm going to make a channel of strings. I'm going to send hello across the channel, and then I'm going to try to receive from the channel and output it to the terminal. Naively, we might expect this to work and just output the word hello, but we're actually going to get deadlock again. This is because the send will block until something is ready to receive, but the code never progresses to the receive line because we're blocked at send. To make this work, we'd need to receive in a separate Go routine. Alternatively, we can make a buffered channel by giving a capacity when we make the channel. You can fill up a buffered channel without a corresponding receiver, and it won't block until the channel is full. So with a capacity of 2, this will work and it'll output hello. We can even put 2 things into the channel before having to read anything back out. So we put 2 things in, and then we read them, and nothing blocks here. If we try to send a 3rd time though, the channel's going to be full. So that call will actually block and will get deadlock again. The final construct that Go has is the select statement. If I have 2 Go routines,
Absolute pleasure to be here for the inaugural GopherCon. This talk is Concurrency Made Easy. If you haven't, no one's met me before, my name is Dave. As Audrey said, I'm a Hubber enthusiast and programmer from Sydney. And if I'm completely honest, this slide is here so that the timer starts in Keynote correctly. So for my talk, I want to continue with the theme of concurrency that some of the previous speakers have touched on. And as someone who's had the privilege of talking to programmers who are considering adopting Go, I find that a common motivation amongst many of them is they want to take advantage of this parallelism that's inherent in our modern hardware. And similarly, in my self-appointed role of a developer advocate, when I meet people who've learnt Go, one of the more common things they say after they've been writing Go for a year or so are kind of things like this. I mean, show of hands, does this resonate? Do these quotes resonate with anybody? One person at the back, you're honest? Yeah, okay. Now, if you've learned Go formally, like maybe you've taken a training course or you've studied it in a book, you might have noticed that the concurrency section is usually towards the back. I mean, this is certainly true of my own material. So clearly there's a disconnect between the concurrency primitives that the language offers and the expectations of some, maybe many, who come to the language for exactly those reasons. I mean, there's kind of a dichotomy. The headline feature of Go is our simple, lightweight concurrency model. And as a product, like the language really sells itself on this alone. But on the other hand, we have this narrative that concurrency isn't actually as easy to use as we make out. I mean, otherwise, authors and trainers wouldn't make it the last chapter in the book, and we wouldn't look back on our formative efforts, perhaps with regret. And this is kind of a shame because I believe that the Go concurrency model is one of the simplest available.
Hi, my name is Matt Holliday and welcome back to my class on programming in Go. So I'm going to start with concurrency in Go. I had a section on concurrency, but now I'm going to talk about how we do that in the Go programming language. I'm going to introduce something called communicating sequential processes. Now, it's an idea that goes back to the 70s, but it's not shown up in a lot of actual programming languages. It's an important feature of Go because it provides us a powerful and simple model for solving a lot of basic concurrency problems. And the features in Go that do that are channels and Go routines, which I'm going to show you also in this section. I want to start with channels. A channel is like a Unix pipe, and if you're not familiar with Unix pipes, it's a way of sending data from one program to another. Typically on the command line, you type a program name and a vertical bar in another, and it redirects the output from one program to the input of another. Now, what's interesting about it is that the programs run in parallel, more or less, or at least they run concurrently, depending on your hardware. And as data comes out of the first program, it's read by the second program. These pipes and channels in Go, for example, have a couple of properties. One is the stuff goes in one end, it comes out the other, so they're unidirectional, and stuff comes out in order. And it keeps coming out until the writing end is closed. The important difference is that in Go, it's safe to have multiple readers and writers for a pipe. Okay? Normally on the command line, there's really no way to actually have multiple readers and writers on a pipe between programs. But when we set up channels in Go, we're going to see that we can have multiple readers and writers. Now, when I talked about concurrency, I said, hey, you know, if multiple people can read and write things, we get into trouble. But actually, the fact that channels are safe for this purpose, that solves a lot of our underlying concurrency problems if we use them. The second thing I want to introduce is the notion of a sequential process. And this is sort of like a classic thing in computer programming, right? I've got a loop, read some data, do some calculation, write some data. So if you think about it, if I run grep on a text file, I have a loop in there. It reads a line, looks to see if the line matches, and if it does, prints it out. Or maybe it's the inverse. If it doesn't match, it prints it out. Okay, so we're doing things 1, 2, 3, and then we go loop around and do them again in that order. And there's not really any concurrency in it. We don't think about it that way. The interesting thing happens when we put these two parts together, right? We have sequential processes talking through channels. The channel is the communicating part of the communicating sequential processes. And what it does is acts as either a buffer or a synchronization point, allowing these sequential processes individually to be concurrent as a group. Okay? And if you go back to the Unix pipe example, the first program writes something, the second program reads from the pipe, first program writes some more, second program reads some more. It's going on, but exactly when they read and write doesn't have to be necessarily at the same instant. And so the flexibility of these channels allows us to say, hey, these things can be scheduled. So each of these sequential processes, it doesn't think about concurrency in itself, but as we throw them across multiple cores, they can be scheduled in a way where the result is a concurrent or even a parallel program. They can sort of run in parallel as data flows from one part to the next. Why is CSP valuable? Okay, so concurrency is always hard. I mean, we just didn't evolve to do that in our heads any more than we evolved to do third semester calculus at 8 o'clock in the morning. But the CSP model can make it, in a lot of cases, less hard. It allows us to write asynchronous code in a synchronous style, and that's very powerful. And I think this quote from Andrew Gerrand is really to the point. Okay, we can do some very simple things in this model of, hey, I write something and it sends a message to something else, and how the messages get scheduled and how these somethings get scheduled across the CPUs is not my problem, it just works. So one of the key components in Go is the Go routine. And the Go routine is just a play on words. It's coroutine, but we use the Go keyword in Go to start it, and so it got named a Go routine. Very clever. Okay, it's really easy to start a Go routine. We just put the Go keyword in front of a function call. And that function call actually starts an independent thread of execution in the program. Okay, I probably shouldn't have used the word thread because a Go routine is not a thread. In fact, a Go program can have tens of thousands of Go routines, and Go will take care of the scheduling them properly on however many threads it needs based on your CPU hardware. Now, there is a catch, and we'll be talking about this as we go along, all through this whole section on concurrency, this and the following segments. And that is, when we start a Go routine, we have to think about what stops it. Okay, the number one way to get a memory leak in Go is to end up with a Go routine leak. And that is a Go routine that's become orphaned. It's stuck, it's not going to finish, and it holds on to the resources it has. And if you're building a server, that kind of leak is bad. And we'll talk about how not to get there. So the other piece in Go is the channel, which is actually a data type, and it represents a way of communicating. If you're familiar with Unix pipes again, it's like that. It's a one-way channel. You put stuff in one end, it comes out the other, okay? And it comes out in the right order, and eventually you can close one end of it to signal to the other end that there won't be any more data. But it's safe for multiple readers and writers. Now, a channel can really have two purposes. Okay, if you think of it as a communication tool, obviously we can pass data through it. And that's a very powerful model by itself. We talked about, sharing in a concurrent program is bad. And so an alternative to sharing is that we actually transfer ownership of data. So I have, say, one Go routine, think of it as a sequential process that generates some piece of data, sends it through a channel to another. And by sending it, it's like I'm giving up ownership. It's yours now. And in theory, as long as only one Go routine has that data at a time, then the race conditions we talked about aren't really a problem. So we can think about a way of transferring data and transferring ownership. It also has a role as a synchronization tool. And that's something we'll get at. But sometimes we need to actually think in a concurrent program about the concurrency. And the fundamental relationship in concurrency is this notion of happens before. One thing happens before something else. Well, with a channel, that's kind of simple, because anything you receive has been sent, right? The send has to happen before the receive. Now, we're going to get into more detail on exactly how that works in a later segment, and there's differences between whether the channel is buffered or not as exactly how that works. So, but I just want to put it out here now as a starting point that one of the things about a channel is it can be used only to really communicate the idea of something is done. I want to very briefly illustrate that with this slide. Here's our partial order, but think about this now as, parts of a program with channels between them, right? There's a happens before relationship. The arrow from 1 to 2A, right? Anything coming into 2A, it happened before in 1, and 2A happened before 2B, and so on. So again, there's a notion of channels can help us when we do want to think explicitly about concurrency. They can help us deal with the happens before relationship. So I'm now going to move back to my laptop, and we're going to start actually building out a program. I want to use some channels and go routines to get the idea across. And the first thing we're going to do is parallel get through HTTP, right? We did this exercise where we went to XKCD and we had to get 2,400 pieces of metadata about comics, and it was slow because we did them one after another. Well, we don't have to do them one after another. We can do them in parallel. And so that's what I want to demonstrate now. All right, I need to start out with some piece of data I'm going to pass around. And we're going to call it a result.
Hey, welcome back to another video. My name is James from Nerd Academy, and in this video we're going to learn the very basics of Go routines. Go routines allow us to write concurrent programs in Go. Things like web servers handling thousands of requests, or your phone rendering animations and making network requests in the background are a couple examples of concurrency. I'm not really going to get into concurrency in this video, just of how Go routines work. There is a good talk by Rob Pike on concurrency and parallelism. I'll leave a link to that video in the description if you want to check it out. In Go, each concurrent task is a Go routine. And when you run a Go program, the main function is actually a Go routine. We call that the main Go routine. Creating a Go routine is actually quite simple. There's a lot of basic examples I can show you right off the bat, but let's start with something a little bit more complicated. Let's create a TCP socket, and any connection to that TCP socket will receive a timestamp every 1 second. Let's go ahead and open up our code editor and take a closer look. All right, so let's open up our code editor, and let's make a new file. We'll call this time server, and in here I'll make main.go, call this package main, func main. All right, so we're just gonna make a simple TCP socket. If you wrote one in C, it's kind of the same idea. So we're going to use the net.listen package. So we're going to have a listener and an error, and that's going to be the net.listen. And we're going to use TCP for our TCP socket, and we're going to listen on localhost, and we'll just use port 9000. Awesome. And if there's an error, we'll go ahead and print that out, and then we should go ahead and return, or actually probably need to exit. Now we just need to wait and listen for any TCP connection on port 9000. To do that, we need a basically forever loop, and we're going to get a connection and another error, and we're going to set that equal to listener.accept. If there's an error here, what we really want to do is just continue to the next, but we'll go ahead and log out the error just to see what the error could be. Otherwise, we're going to write out the time. And to do that, we'll have a function. We'll have an anonymous inline function be automatically executed. And we're going to have another error possibly. So this is going to be io.write string. We're going to write to the connection that was just made. And we're going to write time.now.format. And we'll do 24-hour clock, minute, and every second. And then we'll pass a new line. If there's not nil, then there's some kind of error here, which probably means the connection was broken. Probably a broken pipe error. So we'll just return out of this. This will just return out of this function here. And then we'll go ahead and sleep for September. No, we're going to sleep. Wake me up when September ends. Oh gosh. We'll sleep for 1 second, and then that way it will print out the time every 1 second. Okay, at this point, we're ready to run it. So let me go ahead and open up a terminal here. Go to the time server, run main.go. Our TCP socket should be set up and listening on port 9000. I'm going to use the netcat command and see there is probably a package available on your operating system. For me, it's going to be nc localhost and port 9000. All right. Okay, that didn't work. Why is it? There we go. I forgot to wrap this part in a for loop because it's only going to do it once. We need to do this a bunch of times. There we go. Let's run that again. There we go. Every 1 second we'll receive a timestamp. Now, let's say someone else wants to connect. Let's do the same command again. Nothing's happening. This one's still receiving, but this one's not. That's because this function, as soon as we get a connection, it's kind of blocking. It's not allowing any other connection. So if we stop this one, the other one picks up. And if we rerun this one over here, nothing's going to happen until we stop this one on this side. And there you go. So it is not a concurrent server, which is usually not a good thing. So like I said, writing Go routines is actually really simple. Two letters, one word, go. That's it. Let's rerun this. Rerun it there. Getting the time. Run it here. They're both getting the time at the same time. Pretty amazing. Pretty easy. Yes, it really is that easy, but there are catches. Let me illustrate. Let's make another one. We'll call this, we're going to do a simple countdown. Main.go in here. Package main. Func main. We're going to have a simple method that's literally just going to count down. Func countdown from an integer, and that's all it's going to do. So as long as n is greater than or equal to 0, we're just going to print it out. Print line, and then we'll decrement n, and that'll be it. We should add a little sleep in there because it'll go really fast. We'll use time, sleep, time dot, how about we'll do a half a second. Millisecond times 500, there's your half a second. Awesome. So now we're in our main Go routine here. We're going to
What is going on, everybody? Welcome to part 19 of our Go language programming tutorial series. In this tutorial, what we're going to be talking about is kind of building off the last tutorial, which is concurrency in Go, specifically with Go routines. So in the last tutorial, we started to show some examples of Go routines and how easy they are, at least at the basic level, to get them to do cool stuff. We started to talk about some of the issues that we're going to have right out of the gate when we actually start to try to use these in practice. The main one in currently being that when we run everything as a Go routine, nothing is blocking, therefore we're using like a sleep to make sure the Go routine's finish. Well, this is not really ideal. So instead what we're going to do in this tutorial is work with the sync package. So we're going to go ahead and import sync, and then from here we're just going to define a starting variable. So we're going to say var, we're going to call this WG, which is just going to be short for wait group. And what it's going to do for us is basically this is going to be sync.wait group type. And what we're going to be able to do is specify hey, we're currently working on a Go routine, we want to wait for this Go routine. So every time you have a Go routine, you'll just kind of add one to your wait group, and then every time a Go routine is done, you'll notify the wait group, okay, we're done. And then that way you can actually wait, because for example, it won't necessarily always be the case that you just want to run some Go routines and then you're done. Right? There's going to be times where maybe you want to run some Go routines, wait for those Go routines to finish, and then run some more Go routines, right? So it's not just about, hey, let's make sure these just execute in our program once or whatever. There's going to be lots of ways that you're going to want to synchronize Go routines. So this is one of the ways. So anyways, once you've defined your wait group here, what we're going to do is we're going to come down to the main. And basically, every time right before you start a Go routine, you just add one to the wait group. So we'll just add one there. We'll add one here, and then at the end here, we're just going to do wait group dot wait. So what it's going to do is it's going to wait until these finish, and I'll get rid of the sleep as well. So one thing to consider is, well, how's it going to know when it's done? Well, what you're going to need to do is you're going to need to notify the wait group when things are done. So basically, when this for loop is done executing, it's done. So we're going to do WG done. And now what we're going to do is we can save this. We can come over to our program here, and we can run this. Cool. And so it's done. We didn't waste any time with sleeps. We didn't, we didn't add too much time to sleep. We also didn't miss out on anything. Everything ran in the order that we expected and all that. And so, just to exemplify this, hey there. We'll just add a hi here. Let me save that. Let me add a wait here. Save that again. Let's run that. So as you can see, this is kind of a way that we've synchronized these now, because we're waiting after these two, and then we add another one, and so then that one just runs together. So what if we instead, we could have removed this wait, and now they'll run with each other. So hi, hey there, hey, hi there, hey, hi there. Anyway, cool. Super basic kind of addition to our Go routines, but now we've kind of run into another issue. What would happen if somewhere along the lines we hit some sort of error, and this code just kind of panics out or whatever, and we never actually get to tell the wait group that we're done? Well, we're going to be waiting forever. So in the next tutorial and the coming tutorials, we're going to be talking about, first we're going to talk about the defer statement, and then we'll be talking about panic and
Hi, my name is Matt Holliday, and welcome back to my class on programming in Go. In this section, I'm going to drill down into channels a bit. I want to talk about buffered versus unbuffered channels and get into the difference between channels as a communications tool and channels how they synchronize parts of your program. With that, I'm going to give you a very useful diagram about channel states, and then I'm going to talk about how channels can be used to make a particularly useful structure called a counting semaphore. Okay, so these first couple slides are going to be a little bit of review. I have talked about channel state already a bit in terms of a useful diagram about channel states, and then I'm going to talk about how channels can be used to make a particularly useful structure called a counting semaphore. Okay, so these first couple slides are going to be a little bit of review. I have talked about channel state already a bit in terms of, blocking and not blocking. Right? A channel blocks when you try to send if there's nobody ready to receive. Well, that's if it's unbuffered. And if it's buffered, it blocks because there's no space. Now, on the receive side, it's a little different, right? Obviously, it blocks if there's nothing to read, but you can read from a channel that is closed. And we'll talk about closed channels in just a sec. I've also talked about how channels are unidirectional, and I like that term. There's a couple people running around saying channels are bidirectional. I don't like that because that implies they're full duplex, right? And full duplex means you can send and receive on both ends. Sort of like talking in a telephone. We can both try to talk over each other while listening in effectively. But a channel really has a read end and a write end. Now, what we can do when we pass a channel into a function is we can constrain it by only giving the read end or the write end. And that's useful in terms of information hiding. If I know I'm going to pass a channel to a Go routine that only needs to write it, then I can give it just the write end, and that eliminates certain kinds of problems that could occur in my program, right? It just simplifies things. But a channel is still unidirectional. Everything goes from one end to the other. So closed channels, well, let me step back. Channels are a bit like maps, right? When we went to a map, if it was empty, we could still read it. What we got was a default value. And a map had a two-value read that said, hey, the second value is a Boolean that tells us, was that value actually there, or is it the default value we get from reading empty? So a channel is like that. I can read a channel, and if it's closed, I get the default value. And if I use the to operation read, well, then I get the second value tells me, is the channel actually open, or is it closed, and I'm getting default values from reading a closed channel. You may ask, why is it useful to read a closed channel? And let's put that off for just a sec. Let me jump into the playground because I want to demonstrate this program. It's trivial, okay? I'm going to run it, and it's going to produce the output you expect. And the reason I'm bringing it up, though, is because I can show something else in here. Okay, so I get true if the channel was open, and when I close it, I get the 0 value because it's a channel event, and I get false. The reason I really brought this up here is I want to go back to this notion of unbuffered channels and ask the question, what happens if I run this program, it has no buffer? Now, you should figure it out by now, it's going to block, but actually it's going to do something else. Okay, it's going to crash. And the reason it's crashing is that Go has in its runtime a built-in deadlock detector. All right, now what's deadlock? Well, that's the case where none of your Go routines can make any progress because they're all waiting for something. Here I just have really the one Go routine. It's waiting for a channel that will never become ready. And so the program can't make progress. Now, deadlock is sort of a secondary effect. In a concurrent program, the first thing we worried about was a race condition. And so we use tools for synchronization, like channels and other things, to prevent race conditions, but those can cause problems themselves. And deadlock is the most common problem we get from trying to solve race conditions. We lock our program up so safely that it doesn't actually do anything. Okay. Anyway, Go has a built-in deadlock detector. I wanted to show that. When it can figure out that no Go routine can be scheduled, it will crash your program and tell you, and that's very useful. Now, let me go back to the slides because I want to talk about closed channels again. Okay. Why is it useful to close a channel? Well, that's a tool for signaling. And so I talked about this before, right? One of our problems with Go routines, in fact, the most common problem, is we need to make sure they end. And it's possible to leak a Go routine. We saw that in the last segment. I showed you for about 10 minutes, the most common way to leak a Go routine. So we want to make sure Go routines end, and a useful way to do that is to have some sort.
Hello and welcome back to the channel, guys. In this short video, we will be talking about Go's most unique feature, which is called a channel. So what exactly is a channel? Well, we have already seen what are Go routines. So a channel is a communication object using which Go routines can communicate with each other. You can even understand it as a sort of a pipe which transfers data between Go routines. Go routines can write data into this channel or this pipe, and other Go routines could read data from the other end of this pipe. So without further delay, let's quickly get started with writing some code using channels. The first thing that we will discuss is how do we actually go about creating a channel in our Go program. And it's very simple and straightforward. We have to use Go's built-in make function, which we had also used previously to create slices, maps, structs, and so on. So let me show you how. I simply declare a variable, let me call it ch, and then I say colon equal to make, and then I give the data type. In this case, it will be a channel, chan, which is
السلام عليكم. في الفيديو دوت هنكمل خطواتنا في المواضيع الادفانسد في لغة جو، وهنشرح بالتفصيل وبالأمثلة التشانلز، وهنشوف ازاي نستخدمها في انها تكون وسيلة التواصل ما بين الجو روتينز وبعضها او الجو روتينز والمين ابليكيشن. ودلوقتي let's go. انا اسلام محمود، ودوت الفيديو العشرين في سلسلة جو لانج فور بيجنرز. لو عايزين تشوفوا الحلقات اللي فاتت هيكون في بلاي ليست في الديسكريبشن فيها كل الحلقات. لو عايزين تتابعوا الحلقات اللي جاية ممكن تعملوا سبسكرايب. والنهارده هنتكلم عن التشانلز، والتشانلز حاجه ادفانسد توبيك في جو لانج، وحاجه قويه جدا وواحده من مميزات اللغه. لو استخدمتوها هتشوفوا قد ايه هي قويه وازاي نخلي الابلكيشن بتاعنا ادفانسد اكتر. التشانلز باختصار هي الاسلوب اللي احنا بنستخدمه في ازاي نخلي الجو روتينز يتواصلوا مع بعض. التشانل هي قناة مفتوحة ما بين حد بيبعت عليها رسالة وحد تاني بيستقبل عليها رسالة. والشانل كمان فيها ميزة ان لو حد بيبعت رسالة لازم حد تاني يستقبل الرسالة ديت. مينفعش نكون بنبعت رسائل لوحدنا مفيش حد بيستقبلها. ولو عندنا جو روتين او جزء من الابليكيشن بيستني رسالة على الشانل، الكود مش هيكمل اكسكيوشن لحد ما فعلا رسالة تتبعت. خلينا نشوف مع بعض الكود بيتكتب ازاي وازاي نستخدمها في الابليكيشن بتاعنا. دلوقتي احنا عندنا المين فايل بتاعنا في الباكج مين، وعاملين الامبورت لللايبراريز اللي هنستخدمها. هنستخدم fmt وسync وتايم. احنا هنا عندنا فانكشن اسمها m. الفانكشن ديت بتاخد argument اسمه messages. المسجز ديت الارجمنت دوت نوعه هنا احنا معرفين ان هو نوعه channel string. احنا قبل كده كنا بنعرف بس ان هو نوعه string، دلوقتي احنا بنعرف نوعه ان هو channel نوعها string، بمعنى ان الارجمنت دوت هو channel وسيلة تواصل ما بين الفانكشن ديت و functions تانية او اجزاء تانية من الكود بتستخدم نفس الchannel. فدلوقتي احنا عرفنا ان الchannel ديت نوعها string. كمان دوت بيوضح لنا ان الchannel ليها نوع، هي مش بس كchannel كنوع، بل ان ليها data type للvariables اللي بتتبعت او الvalues اللي بتتبعت جوه الchannel او خلال الchannel ديت. احنا هنا عندنا channel بتستقبل values نوعها string فقط، وجوه الفانكشن ديت في sleep فانكشن بتميميكيت لوجيك زي saving database او importing الفايل او whatever. وفي الاخر بعد ما بتخلص الفانكشناليتي اللي المفروض تعملها هي بتبعت رسالة على الشانل ديت. بتبعت الرسالة او الفاليو اللي هي نوعها string زي ما احنا عرفنا ان هي channel نوعها string، فبنبعت string للشانل ديت. احنا هنا السنتكس دوت بنكتب اسم الفاريبل نيم اللي نوعه channel، والسهم بالشكل دوت معناه ان احنا بنبعت الفاليو ديت للchannel ديت. طيب احنا شفنا فانكشن دلوقتي بتستقبل channel وهي بتبعت عليها مسج. خلينا نشوف المين كود بتاعنا شكله ايه. احنا هنا عرفنا فاريبل جديد اسمه messages نوعه channel string. لو تفتكروا الشورت سينتكس بتاعنا كان دايما بياخد value في البداية، واحنا عشان نطلع الديفولت value من الchannel بنستخدم فانكشن اسمها make. فاحنا هنا بنقول له make channel string، معناها ان الفاريبل دوت اعمل له initialization ويحط فيه default value لchannel نوعها او بتشيل او بتستقبل values الداتا تايب بتاعها string. فدلوقتي احنا عندنا الفاريبل دوت نعمل بيه ايه؟ احنا بنبعت الفاريبل دوت للفانكشن ديت فانكشن m، وبنرن الفانكشن ديت في الجو روتين. دلوقتي احنا هنا اللي بنعمله ان احنا بنقول للفانكشن او للجو روتين دوت احنا عايزين نستقبل منك رسائل، او هيكون وسيلة التواصل ما بين الكود بتاعنا في المين فانكشن والجو روتين دوت من خلال الشانل اللي اسمها messages. فدلوقتي احنا هنا عارفين في السكوب بتاع المين فانكشن الشانل ديت، وجوه الفانكشن عارفة كذلك الشانل ديت. فالرسائل اللي بتتبعت من جوه الجو روتين على الشانل ديت نقدر نستقبلها هنا في الكود بتاعنا جوه المين فانكشن. طيب بعد ما بنعمل ران للجو روتين دوت، احنا هنا بنستقبل رسالة من الشانل ديت. بمعنى ادق احنا هنا هنستنى لحد ما حد يبعت رسالة على الشانل ديت، وبعدين ناخد القيمة منها نعمل لها assign في الفاريبل دوت. فالسنتكس هنا السهم قبل الفاريبل نيم اللي نوعه channel، معناها ان احنا بنستنى رسالة على الشانل ديت. فوق احنا كنا حاطين السهم على يمين الفاريبل، فمعناه ان احنا هنبعت فاليو على الشانل ديت. هنا احنا هنستقبلها، فبيتحط السنتكس ان السهم قبل الفاريبل دوت. فاحنا هنا هنستقبل رسالة على الشانل ديت ونحطها في المتغير دوت. فاحنا هنا عارفين ان الداتا تايب اللي هيكون جوه المتغير دوت string، لان هو دوت نوع الداتا تايبس اللي احنا بنستقبلها على الشانل ديت. وبعد كده هنعمل print للفاليو ديت. احنا كان ممكن هنا على طول نعمل كده، نستخدم السنتكس دوت، يعني احنا هنستقبل قيمة من الشانل ديت او على الشانل ديت، والقيمة اللي هترجع لنا هنعمل لها print. ولكن for now عشان الكلاريتي احنا هنحطها في متغير ونستخدم المتغير دوت، مع ملاحظة ان بما ان الكود دوت بيران جو روتين، يعني بيران asynchronous، بيران in parallel مع المين فانكشن من اول البوينت ديت، فاحنا مش عارفين امتى الرسالة هتتبعت. عشان كده احنا هنا حاطين الويت تايم ال2 seconds دول. فهنا احنا عندنا في ثانيتين شغل هيكونوا جوه الجو روتين. طيب احنا عارفين ومتعودين ان الكود بتاعنا من بعد الجو روتين بيتنفذ بالتوازي، يعني السطر دوت ممكن يتنفذ قبل ما نوصل هنا. طيب هل هنستقبل رسالة قبل ما تتبعت؟ فالحقيقة هنا الران تايم انفايرمنت بتاعتنا هتعمل بلوك للاكسكيوشن للكود لحد ما في رسالة فعلا تتبعت على الشانل ديت. فأول ما الرسالة ديت تتبعت على الشانل، الكود دوت يبدأ يتنفذ في السطر دوت. بعد ما كان بلوك للكود هتنفذ، هنستقبل الرسالة نحطها في المتغير ونعمل print للرسالة ديت. خلينا نعمل ران للابليكيشن ونشوف مع بعض دوت. نفتح تيرمينال جديدة ونعمل ران للابليكيشن بتاعنا. هنلاقي ان في الويتنج تايم ال2 seconds اللي احنا معرفينهم هنا قبل ما السطر دوت يتطبع. لو رجعنا اللوجيك بتاعنا، احنا هنا معرفين الفاريبل مسجز اللي نوعه channel بتاخد داتا تايب string، بعتناها للفانكشن m وبنرن الفانكشن ديت in parallel. فمعنى كده ان احنا المفروض هنبدا ننفذ اللاين اوف كود دوت، ممكن كمان قبل ما نبدا ننفذ اي لاين اوف كود تاني جوه الفانكشن ديت. ولكن بما ان هنا احنا بنقول ان احنا بنستقبل رساله من جوه الشانل ديت، فاحنا هنفضل منتظرين لحد ما الرساله ديت تتبعت. عشان كده انتوا شفتوا الويت تايم اللي هو ال2 seconds اللي جوه الجو روتين دوت. بعدين الرساله ديت اتبعتت على الشانل، وهنا قدرنا نستقبل الرساله، حطيناها في المتغير دوت وطبعناها. ده الورك فلو الطبيعي بتاعنا في التعامل مع المسجز. ممكن زي ما احنا كده استقبلنا رساله من جوه الجو روتين، نقدر نبعت رساله لجو روتين، وهنشوف دوت في الامثله اللي جايه مع بعض. ولكن الاول خلينا نشوف مثال للاستخدام الخاطئ للجو روتينز. هنا المثال دوت هيوضح لنا نقطه ان الكود فعلا بيبقى مستني لحد ما الرساله تتبعت، ويكون مستني لحد ما الرساله حد يستقبلها. خدوا بالكم ان احنا فوق كنا بنتكلم ان الكود دايما بيكون مستني هنا لحد ما الرساله ديت حد يستقبلها، ولكن في الحقيقه هو بيبقى مستني هنا لحد ما حد يبعت الرساله، وهنا بيبقى مستني لحد ما حد يستقبل الرساله. الكلام ده هيوضح لنا في المثال اللي معانا دلوقتي. احنا هنا معرفين متغير نوعه channel داتا تايب بتاعت المسجز اللي فيها string، وهنا بنبعت المسج هاي على الشانل ديت، وبنيجي في السطر اللي بعديه نستقبل الرساله ديت من الشانل ونعمل لها print. هنا اللاين اوف كود دوت هيعمل بلوك للاكسكيوشن لحد ما اي حد تاني يعمل، او لحد ما اي حد تاني يستقبل الرساله ديت. طب احنا بنستقبل الرساله فعلا في السطر اللي بعديها، ولكن الشانلز بنستخدمها وقت ما نكون بنران حاجات in parallel. فمعنى كده ان يكون في حد بيلسن على الرساله في مكان وحد بيبعت الرساله في مكان تاني. ولكن لو احنا بنبعت الرساله وبعدين بنستقبلها في نفس السطر دوت، مش هيبقى ممكن، لان وقت ما نبعت الرساله الكود هيبلوك مستني اي حد تاني في جو روتين في اي ثريد تاني يكون بيستقبل الرساله ديت، ودوت مش حقيقي. مفيش حاجه في جو روتين تاني بتستنى تستقبل الرساله. هيفضل عندنا هنا ديدلوك. لو جينا نعمل ران للابلكيشن ونشوف المشكله هتظهر ازاي، هنلاقي هنا ان بيظهر لنا رساله all go routines are asleep وفي ديدلوك، لان احنا هنا مفيش اي حد فعلا بيستنى يسمع او يستقبل الرسالة اللي اتبعتت على مسجز بالتوازي، لان زي ما قلنا الكود هيقف الاكسكيوشن بتاعه عند السطر دوت ومش هيوصل لللاين اللي احنا بنستقبل فيه الرسالة. طيب هل في كيسز احنا فعلا بنحتاج نبعت رسالة للشانل ونستقبلها جوه نفس الثريد، جوه نفس الجو روتين؟
Welcome to Section 7, Channel. In this section, we'll be looking at what is a channel, of course, how to declare and use channels. We'll look at how you use functions and channels together and what does that mean in terms of passing channels to function and returning channels from functions. We'll look at some more advanced uses of channels, and that would include how do we use channels with coroutine. We'll learn that actually the purpose of channels, this data type that we'll learn about in this section, is really to help us work with Go routines, and we'll see what's the intent there. We'll also look at channel selection when we talk about channels and Go routine. How channel selection makes a lot of things very, very nice and introduce us to some concurrency patterns. And we'll also talk about read and write only channels. It doesn't seem to make sense now, but later on we'll see it how it's important that how you might be able to want to just have a channel that somebody can read data from, or a channel that somebody might only be able to write to. And then finally, we'll wrap up with channels of channels. Every section starts with lecture 1. In this lecture, the topics we're going to cover are what is a channel, simple channel usage, and we'll see how to send and receive data on a channel. So what is a channel? This is from the Golang documentation. It says, a channel provides a mechanism for concurrently executing functions. Now let's stop right there. If you remember, the way we write concurrently executed functions is by creating Go routines, which run those functions. So a channel provides a mechanism for concurrently executing function to communicate by sending and receiving values of a specific element type. This tells us the fact that we see values of a specific element type, that a channel might operate something like a map or an array or a slice, in that there's an element type that you must specify, and every value that you send on that channel must be of that element type. Okay, so you can't mix element type. So if you have a channel of int, you can only send int. If you have a channel of strings, you can only send strings. Then this last sentence says the value of an uninitialized channel is nil, which means that if you just created a channel variable, it's nil. What then is a channel? Let's see if we can understand this visually first before we write some code. Let's say I had a function 1 and a function 2. And so let's say I have these two concurrent functions, and I want function 1 to generate some data. Maybe it's reading data from a file, maybe it's just generating random numbers or something like that. And I want to get that information into function 2. Now, the way we saw we can do that in the previous section is by using a shared data structure, like a map or something like that. But if we instead introduce a channel, what we can do is say that function 1 sends that data through the channel to function 2, or whoever is going to receive on the other end of that function. So here, function 1 is the sender, it sends data into the channel, and function 2 is the receiver. And what we can imagine also is that if our channel is big enough, as I'm trying to illustrate here, we can send multiple pieces of data, and we should expect function 2 to receive the first piece of data that was sent into the channel. So this is usually referred to a FIFO, which means first in, first out. The data that is in first into that channel comes out first, which makes sense, right? You'd expect that if you join a line, the person up front should be service first. If I change the name slightly from just function 1 to producer and function 2 to consumer, you can see how this general idea can be extended where you can just decouple two pieces of code. And any piece of code that sort of produces data that another piece of code needs to consume or work on, you can use channel, especially if they are running concurrently, to decouple exactly how they communicate. And that decoupling gives you the advantage now of being able to have multiple producers right into the same channel and potentially have multiple consumers consume from the same channel. And this is a huge advantage because it means that you can easily scale your application. And the channel takes care of how to move that data between producers and consumers. And all your producers care about is that it's writing into the common channel, and your consumer data is care about reading data from that same common channel. And you don't have to worry about which one receive what data and all this other stuff. So a lot of things are taken care of for you. And we'll see that in a bit. This gives us a nice visual illustration that we can now go and try and write some code. Here I am in my Visual Studio Code editor. The first thing we want to do is look at how you declare channels. And for that, we simply use the var keyword and say we want to create a variable named channel, ch, and it's the type of it. This is the type. Remember, in Go, we have var keyword, variable name or identifier, and then the type. And in this case, the type simply says, I want a